Welcome everyone. Welcome to Colloquium series for DRP 2024. Today I'm pleased to announce our first Colloquium speaker, Tınaz Ekim from Boğaziçi University. Tınaz Ekim is a professor in the Department of Industrial Engineering at Boğaziçi University. She obtained her PhD at EPFL. After a year of postdoc at the EPFL, she joined Boğaziçi University. Her research areas include structural and algorithmic graph theory, combinatorial optimization, computational complexity, and mathematical programming. And today she's going to talk about computing defective Ramsey numbers. On behalf of everyone, thanks again to Tınaz Ekim, and now I'm leaving the stage to her. Enjoy.
Okay, thank you for the introduction. And thank you very much for the invitation and for this nice organization. So today I'm going to talk about how to compute defective Ramsey numbers. This is I'm going to start very slowly introducing Ramsey theory, assuming that not everybody is familiar with Ramsey theory. So I'm going to start with very basic stuff. And then I will introduce defective Ramsey numbers. So it's a variation. And I will focus on two main approaches to compute Ramsey numbers, namely considering these numbers in spatial graph classes and using computer enumeration to find Ramsey numbers. So my talk will be based on our results obtained in 6 different papers. Actually, the last one is now submitted. So we initiated this systematic study with John Gimbel. He is a very nice collaborator, let's say, and he nicely collaborated with all my students. So everybody apart from John Gimbel in this list of co-authors are my former students. I also added some photos of John. He visited Turkey several times. So this is from his last visit. This is from his visit to Istanbul Center for Mathematical Sciences, İMBM, for those who know it. And maybe you recognize some people in here. Okay, he is a nice tourist, very good tourist as well. And he likes being in Turkey in general. So too many photos of him maybe, but as I collaborated mainly with John in all these works, I want to show some of his photos. So who is familiar with Ramsey theory? Who already heard about the famous party problem? I don't know how many of you. Nobody, almost nobody. Okay, good. So it has been introduced by Frank Ramsey. Actually, Ramsey was a very great scientific, and he pioneered many topics in different domains, including mathematics, economy, philosophy, decision theory, game theory, and he died very young. So Ramsey theory was introduced by Frank Ramsey, but mainly developed by Paul Erdős and his collaborators. So Paul Erdős worked a lot on Ramsey theory. So there are a few, let's say, quotations to summarize Ramsey theory before we start in technical stuff. There's a very nice summary that I like quoting every time. Complete disorder is impossible. So that's so we will start to understand what it means when we go into details, but roughly that means that we can find every mathematical object if we search it in a large enough space. Of course, we need to specify what is the mathematical object we're searching for and what is the space and what does it mean large enough. So there are applications in geometry, number theory, and graph theory. And today we're going to focus on the applications in graph theory. Starting with the famous party problem. Well, maybe you have heard about this problem. There are 6 people waiting in the lobby of a hotel. And the claim is that there are either 3 of them who mutually know each other. So every pair in this tree know each other, or 3 of them who do not know each other. And knowing somebody is something symmetric, like if I know you, you know me. Okay. Well, how to prove this claim? We can represent people with vertices in a graph and put a red edge between 2 people who know each other, and a blue edge if they don't know each other. So then the claim becomes, every time you take a complete graph on 6 vertices and you color all the edges either red or blue, then the claim is that there's either a red triangle or a blue triangle. Either 3 people who know each other or 3 people who do not know each other. But this is an example of 6 people and some 2-edge coloring of the related complete graph. And here you can see that, so we should be able to find, for instance, a red triangle between Fred, Charlie, and Evelyn. Actually, you can have both a red triangle and a blue triangle. It's not exclusive. It's either or. Is the claim clear for everybody? Any question at that point? So please feel free to interrupt me and even ask questions in Turkish or English, whatever you prefer. How would you prove that? Well, if we apply a naive approach, we should try all possible ways of coloring the edges of a complete graph using red and blue, 2 colors, and check if in every such coloring we can find a red triangle or a blue triangle, right? That's the most naive way to check the claim. Well, brute force requires so checking all possibilities, as I said. So we have 6 vertices, and every pair is linked with an edge, which is colored either red or blue. So 15 edges, each one colored red or blue. There are 2 to the 15 possible cases to check. Do you think it's a good idea? Well, not really. So can we do something a little more clever? Hopefully, yes. So a very classical approach in this kind of claims results is the following. Well, we start with the pigeonhole principle, which says that take anybody in this among these 6 people, and we can assume that, say, Anne, she knows at least 3 of the other 5 people. Actually, it might be the case that she doesn't know 3 people among these 5, right? And this case will be just as symmetrical. So I'm going to proceed with this assumption. And if it doesn't hold, then the symmetric case is just the same. Similar proof works. So here is Anne, and she knows at least 3 of the others, right? So at least 3 edges, which are colored red, incident to Anne. Now look at the end points and the vertices of these 3 red vertices, edges, sorry. Well, there are 2 possible cases. Either there is, among these 2 people, among these 3 people, either there are 2 links with a red edge, in which case, together with N, that will form a red triangle, or none of them is red among these 3, which means that they're all blue. Then here is the blue triangle, right? Okay, so this mainly proves that the Ramsey number of order 3, is at most 6. So there are, as soon as you have 6 people, there are 3 who know each other or 3 who doesn't know each other. So in terms of 2 edge colorings of a complete graph, it means that as soon as you take a graph on 6 vertices and color all the edges with either red or blue, there's either a red triangle or a blue triangle. Well, the question is 6 best possible? Well, if it works with 6 people, of course, if you have more people, it will be even easier to find a red or blue triangle, right? But what if I have less than 6 people? Is 6 best in that sense? Well, yes. And to show that this is the best possible, we need an example that we call an extremal graph. Here is a complete graph on 5 vertices whose edges are colored red or blue, and it doesn't contain red triangle nor blue triangle. So here we prove that the Ramsey number of order 3, 3 is 6. And actually, instead of speaking in terms of red and blue edge colorings, we can alternatively talk about the graph and its complement. Like a red triangle will be a clique in my graph, and ignore the blue edges, just focus on the red edges, and your graph is the red graph. And we can replace the statement as follows. In every graph on at least 6 vertices, there's either a clique on 3 vertices, this is a triangle, or independent set on 3 vertices, which means that in the complement, right, this is a triangle. Okay, so any questions so far? Okay, every graph on 6 vertices contain either a K3 or an independent set on 3 vertices. Now, what do we know about these classical Ramsey numbers? Well, the formal definition is the following. The Ramsey number of order ij is the minimum integer n such that all graphs with n vertices have either a clique on I vertices or an independent set on j vertices. So in the previous example, we had I equals j equals 3, right? But they can be different. Well, this is the list of the table of what we know about classical Ramsey numbers. Here we have just shown R33 equals 6. In green, you can see all the Ramsey numbers that we know to date for sure, so exactly. And whenever you have 2 numbers in some cell, that means this is the best known lower bound and upper bound. And you can see that the lower bound and upper bounds are quite far from each other, right? So we know very few Ramsey numbers. Okay, actually, as you may guess, they are extremely hard to compute. And there's a very nice saying from Paul Erdős that I like to quote everywhere. He said the following: imagine an alien force vastly more powerful than us, landing on Earth and demanding the value of R55. Let's go back for a while. R55 is the first unknown value here. Okay, it's between 43 and 48. Okay, in that case, we should marshal all our computers and all our mathematicians. Pay attention, we need both mathematicians and computers, and attempt to find the value. But suppose instead that they asked for R66, we should attempt to destroy the aliens. What was the name of the series about aliens? Like unuttum şimdi. Okay, so now there are lots of variations of Ramsey numbers. For instance, in terms of colors, instead of coloring a complete graph using 2 colors, we can color it with more colors, and then again claim that there will be a monochromatic clique on a given number of vertices. Or there are variations in terms of hypergraphs. where edges are subsets of several vertices. Or graph Ramsey numbers. Instead of searching for cliques and independent sets, we can search small graphs, H and F. On this topic, so I'm going to continue with defective Ramsey numbers, but if you are interested in Ramsey numbers, classical Ramsey numbers, let's say, then there's a perfect, I would say, survey, dynamic surveys from Stanislaw Radziskowski in the Electronic Journal of Combinatorics. So he started in 1993, and it's a dynamic survey, so there are revisions. And actually, I just met Stanislaw a month ago at a conference, and he said that now they are at revision 17. So there is a new one. And here he focuses on graph Ramsey numbers, multicolor and hypergraph Ramsey numbers. And at the end, he gives, in the concluding remarks, he gives the list of variations of Ramsey numbers which are not included in this survey. So this compilation does not include much information on these variations, including defective Ramsey numbers. So it's a relatively new variation, which is already in this survey. So I'm happy for this because I like this problem. Okay, let's move on with defective Ramsey numbers then. Well, instead of complete graphs and independent sets, cliques and independent sets, we're going to relax this definition and talk about dense and sparse sets. More precisely, we will say that a set of vertices is k-sparse if this set S, when you look at the graph induced by this set, the maximum degree is at most k. So there's a limit on the maximum degree. Clearly, if you put k equals 0, then you get an independent set. The degree is 0, so nobody has a neighbor, right? Do I need to go more slowly, or is it okay? Like, what is a neighbor, degree, all this kind of, I mean, I'm not defining. So please feel free to interrupt me. Everybody problem, yes. Okay, now I go to the chat and.
There was also another question. I couldn't interrupt you, but if you like to.
Go ahead.
So can we also use topology, like consider the cell decomposition of the two spheres induced by red and blue edges and run a Euler number arguments?
No, it's not. I don't see the any relation with Euler formula, you mean? No, it's not related to graph drawing and the topology, the planar graphs or whatever. Triangle face. Maybe I need to think about this. We can discuss about that later. Okay. Okay, let me continue. So, oops. And we're going to relax the notion of a clique as using k-dense sets. So this is just the opposite in the sense that, so a set will be called k-dense if it induces a k-sparse set in the complement. But maybe an equivalent way, an easier way to see that is it is almost a complete graph, complete set, let's say clique, but we allow every vertex to miss at most k others in this set. So it has to be adjacent to everybody, but at most k others. So here are some examples. Okay, k-sparse and k-dense together, we call them k-defective. So they are defective with respect to their perfect versions of clique and independent set. Okay, here is a graph, and here is in yellow, you can see a set on a 11 vertices. There are 11 of them. And if you look at the graph induced by this yellow vertices, so just look at the yellow degree. Every vertex has at most 2 other yellow neighbors. So this is a cycle here, so their degrees are 2. This is isolated, so 0. This vertex has only 1 degree, and this one as well. These two. So this is a 2 sparse 11 set. Likewise, this green set is 2 dense 4 set. So there are 4 vertices, and every vertex in this set is allowed to miss at most 2 others. Well, vertex 17 misses 16 and 15, so it misses 2 others. 18 doesn't miss any of them, so it's adjacent to all of them among these 4. And these 2 misses only 1, which is 17. Okay, so this is a 2 dense 4 set. Now, we define defective Ramsey numbers as follows. So this will be again, so we added this k here, index, right? Minimum integer n, such that, again, all graphs with n vertices or more, of course, contain either a k-dense I set or a k-sparse j set. So the first parameter is related to the k-dense set and the second to k-sparse. And we're going to call a graph extremal for a given defective Ramsey number here if it has order 1 less and it contains none of these defective sets. So no k-dense I set nor k-sparse j set. So this is the T5 which helped us to prove that R33 equals 6, remember. So that's an extremal graph for R33 equals 6. So F5 cycle. Okay, since a k-defective set is by definition also k+1 defective, we have this relation. Well, it's easier to see this using the classical Ramsey number. So if k is 0, we simply omit it, right? Well, a k-defective set, a k-sparse set, every vertex has degree at most k in here. So it is also at most k+1. So it is also k+1 sparse, right? So as k increases, the Ramsey numbers decrease, possibly. Okay, the first results about these numbers go back to 1999. And in that paper, it was called one dependent Ramsey number, and they only studied one defective Ramsey numbers. So they showed these values. And then, as I said, we started a more systematic study with John in 2013, sorry. And in that paper, we mainly focused on partitioning a vertex set into k-defective sets. But we also showed R255 equals 7. John, with his co-author Glenn Chappell, also studied the asymptotic behavior of these numbers, computed some upper bounds and lower bounds, and started to use some computer enumeration to find some exact values with all extremal graphs up to 12 vertices. With a student of mine, we took these upper and lower bounds. Actually, even though this seems to be published later than our result, actually, it took them a while to publish it, and we were already aware of their results. So our paper has been published before theirs, but uses their results on these lower bounds and upper bounds. First, there are some exact values when so they used A and B instead of I and J in this paper. When the parameters are close to k, so say k+2 or k+3, we can give exact values. And otherwise, they provided several lower bounds and upper bounds. So the first three are lower bounds using smaller parameters. So in a lower bound on RKAB using RK A-1B, etc. And the two last ones are providing some upper bounds, again, using smaller parameters. And what we did with my student is to take these bounds and compute them over and over in an iterative way. So we start with some exactly known values, which provide us some lower bounds and upper bounds, and take the best lower bound and replace it in the other one, etc., etc. So we recursively try to obtain the best known lower and upper bounds on defective Ramsey numbers. And then we use a random graph generator to check if we can find some extremal graphs or sub-extremal graphs to improve the known lower bounds. So as soon as we can find a graph of order the best known lower bound, which doesn't contain any k-dense I set, nor k-sparse J set, then we improve the lower bound by 1. So this will be a candidate for an extremal graph. So we use this and started to form some tables, as I have shown for the classical Ramsey numbers. Here, this is for R1 AB. And okay, the numbers that you see in bold are the improvements that we obtained using this random graph generator. And all the others are computed as the best lower bound and upper bound using the formula given by John and Chapel, Gimbel and Chapel. We did this for R2, R3, R4, 5, and so on. And our conclusion is the following. There's no time limit restriction to enlarge these tables in terms of the parameters using a recursive computation of bounds. So this is a trivial computation. However, for the improvement algorithm using a random graph generation, of course, we can try a lot of graphs, but never being able to improve the lower bound. So we have to say, okay, we stop after given time, which was 8 hours. And we obtained in total 55 improvements for the lower bound. And the highest improvement was by 9. But the main result conclusion from this paper is that we could not obtain any new exact value using these lower bounds, as expected, I would say. So computing exact values for defective Ramsey numbers is extremely difficult. So what can we do? At the time we saw this paper, 2014, about classical Ramsey numbers. In that paper, we considered Ramsey numbers in graph classes. That was a recent approach, a new approach by the time. So, for example, remember the party problem? We showed R33 equals 6 with the extremal graph of 5 cycle is the unique extremal graph. We can also show that. Now, let me ask you the following question. What if I want to know, okay, what will be the minimum order n of a graph, of a bipartite graph? So I focus to bipartite graph classes. What will be the minimum order n of a bipartite graph to guarantee the existence of a clique of size 3 or an independent set of size 3? Well, first of all, there's no clique of size 3 in a bipartite graph. There's no triangle, right? And the unique extremal graph for R33 equals 6, which is the red graph here, C5, is not bipartite neither. So this means that the Ramsey number 33 reduced to bipartite graphs is smaller than 6, actually. It is 5. which means that every time you take a bipartite graph on 5 vertices, you can find an independent set of size 3, because we don't have a triangle of size 3, a clique of size 3. And a 4 cycle is an extremal graph, which shows that, so think of a 4 cycle, it is bipartite, it contains no independent set of size 3. So 5 is the best in that sense. So in the rest, we said, okay, we're going to focus on this. And okay, let me first mention two important results from that paper, still on classical graph Ramsey numbers. Is it easier to compute a Ramsey number in a given graph class G or not? What do you think? So in that case, for R33, it was kind of easier for bipartite graphs, right? Because it reduces the structure, and this helped us to conclude. Well, they show two important results. First, for instance, if we take the class of perfect graphs, or any subclass of it containing disjoint unions of complete graphs, so this is not very restrictive, let's say, then here is the formula for Ramsey numbers. It's very easy. And this basically follows from the definition of perfect graphs. If you don't know, it doesn't matter. But there is at least this graph class, which is well known and well studied, for which it is trivial to compute the Ramsey numbers. There's a unique formula for every I and j. Very nice. But the second important result is that Ramsey numbers restricted to some other graph classes, so they name a few, like claw-free graphs or AT-free graphs or the class of PL-free graphs. So if you don't know these graph classes, doesn't matter. So Ramsey numbers restricted to these graph classes are at least as difficult as determining the Ramsey numbers for arbitrary graphs. Actually, they show that they are equal to classical Ramsey numbers in general. So they're not any easier. So answer to my question is it easier to compute Ramsey numbers in a given graph class? Well, it depends on the graph class. So we said, okay, can we find graph classes for which we can give such formula for defective Ramsey numbers, where it becomes easy? Okay, but let me first define formally the defective Ramsey numbers in a graph class. So this will be the minimum integer n such that all graphs in the given graph class G of order n contain either a k-sparse I set or a k-dense J set. And then an extremal graph, we also require it to belong to this graph class. Well, what is a graph class? This is just a set of graphs defined by a property. I'm sure you already know of some graph classes. So bipartite graphs is one of them. What else? Trees, you know, trees for sure. But there are thousands of graph classes defined for different motivations, let's say. Okay, so as we have observed for classical Ramsey numbers, the same applies to defective Ramsey numbers. When we restrict our attention to a given graph class, the related defective Ramsey number is less than or equal to the not restricted case. Okay, we first focused on perfect graphs and one defective Ramsey numbers. And we could compute some defective Ramsey numbers as here. So R1, 44 to 48, and then R1, 55. And here we used classical proof techniques, which are mainly considering the neighborhood of a specific vertex, like the one in the party problem proof, right? And using structural properties of perfect graphs. So we we know a lot of nice properties of perfect graphs, like they don't contain any odd cycles, induced odd cycles or complements. And in that paper, we also used for this last number, R155, computer-assisted proof. How? Well, we took all perfect graphs of order 9, which are provided by McKay online. But you may guess there are a lot of them. I will talk about this issue. And then we added a new vertex in all possible ways. Then check if it contains one defective 5 sets, one sparse or one dense. And again, check for perfect. So this is a computationally very, very heavy. And if it doesn't work, then we add one new vertex, etc. And we went up to 30, which means that we could still find some perfect graphs on 12 vertices, which contain no one defective 5 set. But we also checked all graphs on 13 vertices. We checked them like this and didn't find any one defective, didn't find any perfect graph who doesn't contain a one defective 5 set. Okay. Then we moved on exact values in graph classes. So it was a work with Yunus Emre Demirci and Mehmet Akif Yıldız. So nicely enough, in forest, we could find a simple formula, a unique formula. So this is these are graphs, every connected component of which are trees, or cographs. So these are graphs who doesn't contain paths on 4 vertices in an induced way. Again, there's a nice formula, unique formula for all cases. And this is what we have done. So I'm not going to go into details, but just to let you know, in yellow, cactus graphs, in green, bipartite graphs, and in blue, split graphs. And the first column here says the conditions on I and J parameters, and then we have different cases for K equals 1, 2, 3, or at least 4. Well, for cactus graphs, we could solve almost all cases, let's say, except for K greater than or equal to 4, and with this phi equals K plus a very special case, let's say. So this is open, but the rest is solved. For bipartite graphs, again, we could solve most of the cases. So here there's an interval for I for which it's open. And here there's only a few values for which we could conjecture something. Okay. And lastly, for split graphs, again, we have nice formula which we conjecture is valid for the cases we couldn't show. Well, now, how to use computer enumeration for defective Ramsey numbers? Let me check timing. Okay. So I will try to show you the challenges, the main challenges in this kind of research without going into technical details because we don't have too much time for this. Well, to show that the k-defective Ramsey number in the graph class G is n, we need to do 2 things. First, show that all graphs of order n in that class has a k-dense R set or a k-sparse J set. So enumerate all graphs of given order and check for this. And then show that there's at least one extremal graph of order 1 less n minus 1 in that graph class, belonging to this graph class, and having no k-dense R set, I set, nor a k-sparse J set that we call forbidden defective sets. Well, the first problem is that there's a huge number of graphs of order n. So if we take order 11, this is the number of non-isomorphic graphs. And even if we restrict our attention to a graph class, say perfect graphs, there's still a huge number of them. And imagine we need to consider every single one of them and make additional checks. And the graph isomorphism problem is a very hard problem. So in our further research, we used NOTI, which is the best known isomorphism check algorithm. But it's not very easy to use. But if you want to do something competitive, let's say, it's a must. And so we went on with some subclasses of perfect graphs and proposed a generic algorithm to compute Ramsey numbers, defective Ramsey numbers in graph class. Here is the main idea. Well, we start with a set of graphs on n vertices, which has no forbidden k-defective set. So by this, I mean k-dense I set or k-sparse J set for given parameters I and J. So we start with the input set, which is, as we call, sub-extremal. And the output will be all graphs on one more vertices, again, belonging to the desired graph class G, and which has, again, no forbidden k-defective set, and containing at least one graph from the input set as an induced subgraph. So we start with a small set of graphs having the desired properties, so candidates for being extremals, but smaller, and we enlarge them, and we only keep those which are still candidates for being extremal. Here is how it goes. So for each vertex in the input set, we will construct a new graph by adding a new vertex in every possible way, because we need to check for every graph, right? Then we need to examine all subsets of the new graph containing that new vertex, because the previous subsets were okay. We have already checked them. They have the desired properties. And eliminate those containing a k-dense I set or a k-sparse J set, because we're not interested in those. We want to construct extremal graphs at the end of this algorithm. So add those graphs belonging to the graph class among the remaining ones to the output set. So this is another requirement. We want only graphs in the desired graph class. And at the very end, check isomorphism to return a maximal set of non-isomorphic graphs. We don't want to return the same graph over and over. Well, there are several issues here. This is generic, and the efficiency depends on several implementation details. Well, adding a new vertex in every possible way, checking all subsets containing this new vertex, and checking whether the obtained graph belongs to the graph class. This is what we call graph recognition problem, whether the given graph belongs to the given graph class or not, and isomorphism, of course. So how do we use this generic algorithm? We start with simply an isolated vertex, because any extremal graph will contain isolated vertex. And then apply the algorithm in a repetitive way by taking the output set O of one iteration as the input set for the next iteration. And we're going to stop when the output is empty. At that point, it means that we have reached the desired Ramsey number. So it will be n plus 1, where n is the order of the graphs in the last input set. And this last input set is the set of all extremal graphs with n vertices for R, K, V, I, J. And the graphs at earlier iterations are called sub-extremal, the name of the algorithm, because they are simply candidates for being extremal, but we don't know yet where they are extremal or not. Okay, to implement this in an efficient way, we need to perform the recognition algorithm for the graph classes efficiently. And to do so, we need to take advantage of the structural properties and characterizations of the graph classes. I'm going to give 2 examples where we can do this very efficiently using such characterizations. And we can even skip the recognition phase if we make sure that we only generate all graphs we only generate graphs belonging to the class, but we also need to make sure that we generate all of them. We don't miss any. So this requires very powerful structural characterizations of the graph classes. That comes from structural graph theory. And we also make use of the fact that the new graph is obtained from the old one by adding one new vertex. And the old graph was good. It had all the nice properties, desired properties. So if the new graph has a problem, it is because of the newly added vertex. So we can also try to take advantage of use this fact. Okay, and the isomorphism checks is most of the time the most time-consuming part of in this perfect. In the case of perfect graphs, it was the most time-consuming part. Okay, perfect graph recognition. Well, we know, so we need to be able to check if a graph that we constructed is perfect or not. It is known that there's a polynomial time algorithm for this, but it is highly polynomial, n to the 8. So we prefer not to use it. Instead, we used an exponential time algorithm, which uses a brute force based on the strong perfect graph theorem, which says that a graph is perfect if and only if it contains no odd holes. So we basically check this using an explicit enumeration, and it works better when n is not too high, the number of vertices. And we could obtain these two numbers as a combination of computer enumeration and direct proof technique. Well, how? It turns out that the computer enumeration, the algorithm couldn't go up to 19 or 22 because of it was too time consuming, but we could obtain only a few sub-extremal graphs and complete the proof by hand. So it's a combination of computer enumeration and direct proof techniques. Okay, here we could obtain all defective Ramsey numbers in perfect graphs with value at most 15 in less than 4 hours. Note that, so Mackay is known for the for providing the best enumeration algorithms and best isomorphism checks, or which are related to each other. And he gives lists of all non-isomorphic perfect graphs up to only 11 vertices. So it wouldn't be possible to take these 11 vertices and check defective sets inside for every subset. So we wouldn't be able to go up to 15 for values because the list goes up to 11 vertices. Okay, and this is the list, the tables that we could form using this generic algorithm. So here, the numbers in parentheses are the numbers of extremal graphs. How many non-isomorphic extremal graphs we have. And whenever we put in bold, this is a result obtained in that paper with Akif, Yılmaz, Yıldız, and Yunus Emre Demirci. And if it is not bold, it was known before, so it follows from some of the previous results. Then we apply this algorithm to bipartite graphs and chordal graphs. Well, bipartite graph recognition is very efficient. You simply need to start from a vertex and label all its vertices neighbors minus, and then the neighbors of these plus, and so on, right? So I'm not gonna show the tables, but we could obtain tables for our 2, 3, 4 with all values up to 15 in less than 5 minutes. So here we could even enlarge these tables more. It goes very fast. Actually, this helped us to show that our own previous conjecture was false about, remember these few values for which we don't, so in the table, big table, the only values for our 1 in bipartite graphs, which were not known, we have conjectured to j minus 1, but these computations show that they are not true. Then chordal graphs. What happens in chordal graphs? So for those who know chordal graphs, they have very nice, very nice properties. One of which is the perfect elimination ordering, which says that a graph is chordal if and only if we are able to order its vertices such that every vertex, when you look at its neighborhood in the upcoming vertices, it's a clique, this neighborhood. And this helped us to generate only chordal graphs and all of them in the generation process. So we skipped completely the recognition phase. So add a new vertex, not in all possible combinations in the generic algorithm, but by making it adjacent to all possible cliques. So this if and only if characterization here helped us use this result and make it very efficient and skip completely the chordal graph recognition step. And therefore, we could go up to values 20 in less than 12 hours, or values up to 15 in less than 5 hours. Again, Mackey lists all chordal graphs up to only 13 vertices. So we could go further. Lastly, so I'm gonna, this is the last result I want to mention. We apply this idea to triangle-free graphs. So here we have no triangles. Well, if there's no triangle, there's no clique of order 3 or more, right? So no triangle, no big cliques. Likewise, if there's no triangle, we could show, first we show that we don't have large k-dense sets. And how large? Well, it depends on k. So if k is 0, so independent set, right? Sorry, clique of size 3. But if for other case, it's 2k plus 2. And this bound is best possible using some Tınaz graphs. Actually, we can show that. Well, this means that the Ramsey number, so this is my notation for triangle-free graphs, in triangle-free graphs, will be the same for all I prime greater than or equal to 2k plus 3, because there is no such set, dense sets. So that means that we mainly focus on Ramsey numbers, defective Ramsey numbers, where I is between k plus 2, because if smaller, it's trivial, and at most 2k plus 2, between these two values. And most importantly, we should focus on sparse sets. Like there's no clique or no dense sets in triangle-free graphs. So we can introduce a similar parameter that we call tkj. So we just get rid of the clique part, the dense part, because the minimum integer n such that every triangle-free graph of order n has a k-sparse base. And we used our generic algorithm. Okay. In direct proofs, we used some structural results, so I'm not going to go into details. Like, just take a vertex and look at its neighborhood. Since there is no triangle, the neighborhood is independent. And this helps a lot. And in computer enumeration, we used parallel computation, both in the graph generation phase and isomorphism checks. So thanks to my student, who's very good in implementing in coding, we could make a parallel computing using NOTI. And there's no triangle-free recognition phase again. Well, you have a graph with desired properties. Now you add a new vertex in all possible ways, but you don't want triangles. All you need to do is to select the neighborhood of the new vertex as an independent set. because as soon as there's an edge in its neighborhood, when you make it adjacent to both endpoints of this edge, well, you will get a triangle. So this speeded up a lot our implementation. So we could compute defective Ramsey numbers up to 18 in less than 2.5 hours and obtain such. Okay, this is the last part, which will also be my conclusion, actually. So these are the T, K, J values that we obtained. And from computation to conjecture, these tables helped us to formulate some conjectures. Well, this is the conjecture. Tk, k plus I equals k plus 2i minus 1. Well, this is, when you look at the diagonal, like in green here, orange diagonal, and then yellow, then blue, it follows this formula. And we can also see that complete bipartite graph with I minus 1 vertices in one side and k plus I minus 1 in the other side is an extremal graph every time. Now, this is quite interesting because if you fix k, look at k equals 6, so this yellow arrow here, starting from the diagonal, well, k is fixed. So as I grows and j equals k plus I, and we use j in these tables, well, you have 9, 11, 13, 15, 17, plus 2 every time. So it grows linearly. And this is extremely unusual in Ramsey numbers. This is too regular. And we also know that this trend doesn't continue as n grows. We could show that Kn grows at that rate, n squared over log n for fixed k. Okay. So this is from computation to conjecture, but we also have from conjecture to theorem, because we could show the orange diagonal. So the orange diagonal corresponds to the conjecture for I equals 2. And we could show this result. We could also show the yellow one for I equals 3. And as you see, for I equals 3, so the yellow diagonal here, there are always exactly 2 extremal graphs. And we could show that these 2 extremal graphs are those graphs. And there's no other. Again, this is very, very unusual. And here, we could also show the blue one. And here, again, there are exactly 7 every time. I have never seen such a regular pattern in Ramsey numbers. And actually, it's not very hard to show that there are exactly 7, even theoretically, because they are all obtained from a complete bipartite graph, removing some edges, like the previous one. And okay, this is all theorems that we could obtain, but you see the green diagonal here, 46, again, the same number all the time. This is extremely surprising. Yeah. Okay, so let me see if I don't miss anything. Oh, okay, maybe just one more thing, then I conclude. So we could show these 3, okay, but it doesn't seem that we can show the whole conjecture with the same approach, because every time I grows, there are more cases for the degrees of the vertices to consider. So to show this for all i's, like as claimed in the conjecture, we will have more and more cases to consider every time, and it doesn't seem to be very feasible, let's say. Okay, so research directions as conclusion. Well, computer enumeration and classical proof techniques are in a nice interaction. I think they interact very nicely. And computing some new values with computer can refute some conjectures, as we have seen some examples. But we can also observe some patterns in the computed numbers and formulate related conjectures, which can then turn into theorems. And actually, we could observe some patterns in the structure of extremal graphs for other extremal problems as well, that we could generalize these patterns, so in the construction, and which provide lower bounds for large defective Ramsey numbers. So there are still a lot to do in this direction, and the first of which is efficient enumeration of graph classes. For many graph classes, we don't know how to efficiently enumerate all graphs belonging to this class for a given number of vertices, of course. And another direction which is promising is the use of integer programming. This is more industrial engineering method, but maybe you are also interested in this. Recently, it has been used for improving best known lower bounds for classical Ramsey numbers. And we also use this for triangle-free graphs. If you want to use it in graph classes, it depends very much on the graph class, actually, whether you can formulate the recognition problem as a set of linear equations or not. It's a little tricky, but I think there are a lot to discover in this direction as well. So that's my conclusion, and thank you very much for your attention. Ready for your questions.
Thank you so much. So let's applause our speaker and thanks our speaker. Are there any questions about the presentation?